Today, we will look at some problems about water hammer phenomena in pipelines and centrifugal pumps. For the first problem, we need to determine the minimum valve closure time that would prevent a large pressure rise. And we know the rapid closure valve closures are those in which time less than or equal to times L divided by C. And we know the C equals C is the speed of the pressure wave, square root of the EC divided by the density. And we also know 1 over EC equals 1 over EB plus D times K divided by EP times E. So we need to solve the EC first, and then we can determine the C and solve this problem. So from the problem, we know the EB equals 1.5 times 10 to the power of 9 Newton per square meter. And also know this is a steel pipe. So from the table 4.1, from the table 4.1 in the textbook, we can get that the EP equals 1.9 times 10 to the power of 11 Newton per square meter. And we know the wall thickness for this pipe is 2.5, so we know that E equals 0.025 meter. And we also know the diameter of this pipe is 0.5 meter. And we know the pipe with expansion joints, so we can use this equation. The K equals 1 minus 0.5 times epsilon. This equation is on the page 126 to calculate the K. And we need to note that for the common pipe material, epsilon equals 2.25 is often used. So now we can calculate the K equals 1 minus 0.5 times 0.25, so the value is 0.875. So now we can calculate the EC. So the EC 1 over the EC equals 1 over 1.5 times 10 to the power of 9 Newton per square meter plus 0.5 times 0.875 divided by the 1.9 times 10 to the power of 11 Newton per square meter times 0.025 meter. So we can get that EC equals 1.32 times 10 to the power of 9 Newton per square meter. And now the C equals square root of the EC divided by the density equals square root of 1.32 times 10 to the power of 9 Newton per square meter divided by the density. How do we get the density for the oil? Since the problem give us the specific gravity for the oil is 0.85, so we know the specific gravity for the oil is 0.85, and the relationship between the specific weight and the density, the specific weight equals the specific gravity equals the density of substance divided by the density of water. And since the problem didn't give us a water temperature, so we'll always assume that the temperature is 20 degrees Celsius. So at the 20 degrees Celsius, the water density is 998 kilogram per cubic meter. So now C equals square root of 1.32 times 10 to the power of 9 Newton per square meter divided by the 0.85 times 998 kilogram cubic meter. So we can get that the C equals 1250 meter per second. And now we know the 2 times length divided by C equals 2 times the length, although is 1250 meter. The problem give us, and divided by the C, 1250 meter per second. So we know the time equals 2 seconds. So if the valve close faster than 2 seconds, it is a rapid closure and produces the greatest pressure rise. So we have done this problem. For the second problem, we need to determine the maximum water hammer pressure if the valve is closed in 1.5 seconds. So for the rapid valve closure, we know the maximum pressure created by the water hammer phenomenon delta P equals the density times C times the initial velocity in the pipe. And we also know C equals square root of EC divided by density. And we also know 1 over the EC equals 1 over the EB plus the D times K divided by the EP times E. Similar to the previous problem, we also need to determine the EC first. And on the page 9 in the textbook, we know the bulk modulus of elasticity of water EB varies with both temperatures and pressure, and in the range of practical applications in the typical hydraulic systems, the EB equals 2.2 times 10 to the power of 9 Newton per square meter can be used. And because we know this is a ductile iron pipe, so from the table 4.1 we can know that the EP equals 1.6 times 10 to the power of 11 Newton per square meter. And we know the wall thickness for the pipe is 2 centimeter, so E equals 0.02 meter, and the diameter of this pipe is 0.5, so D equals 0.5 meter. And we also know the longitudinal stress can be neglected, so we know the K equals 5/4 minus epsilon equals 5/4 minus 0.25, since epsilon equals 0.25 is often used, so the value is 1. You can find this equation on page 126. And now we can calculate the 1/EC equals 1/2.2 times 10 to the power of 9 Newton per square meter plus 0.5 meter times 1 divided by the 1.6 times 10 to the power of 11 newtons per square meter times 0.02 meter. So we can get that the EC equals 1.64 times 10 to the power of 9 Newton per square meter. And now we know the C equals square root of EC divided by rho. So the value is square root of the 1.64 times 10 to the power of 9 Newton per square meter divided by the rho. So at the 20 degrees Celsius, the density of the water equals 998 kilogram cubic meter. So C equals 1280 meter per second. And now checking for rapid valve closure. 2 times L divided by C equals 2 times the net. L is, let me see, 1200 meter. So times 1200 meter divided by the C. C is 1280 meter per second. So this value equals 1.88 meter a second. And we know the 1.5 second is less than the 1.88 second. So therefore it is a rapid valve closure. So delta P equals rho times C times initial velocity in the pipe. And we know the initial flow rate in the pipe equals 1.35 1.35 5 cubic meter per second, and when the diameter of this pipe is 0.5 meter, so we can calculate the velocity equals q divided by the pi times d squared divided by 4. So the value is 6.88 meter per second. So now the delta P equals 998 kilogram cubic meter times C is 1280 meter per second, and times 6.88 meter per second. So delta P equals 8.79 times 10 to the power of 6 Newton per square meter. So we finished this problem. For the third problem, we need to determine the required pipe thickness. And note that delta P equals rho times c times initial velocity. And from the problem, we know the flow rate, the Q equals 1.45 cubic feet per second. And we also know the diameter of this pipe, D, equals 8 inch equals 8/12 feet. So we can determine the velocity equals Q divided by the pi times d squared over the 4. So the velocity equals the velocity equals 4.15 feet per second. And we also know the water hammer pressure delta P equals 250 pounds per square inch, and at the 20°C, the density of the water rho equals 1.94 slag per cubic feet. So now we can determine that C equals delta P over the rho times velocity. So equals 250 pounds per square inch times 144 square inch per square feet, and divided by 1.94 slag per cubic feet times 4.15 feet per second. So the C equals 4,470 feet per second. And we also know the C equals square root of EC divided by rho. So 4,470 feet per square per second equals the EC divided by the 1.94 slag per cubic feet. So we can get that the EC equals 3.88 times 10 to the power of 7 pounds per square feet. This value also equals 2.69 times 10 to the power of 5 pounds per square inch. And now we can determine the pipe thickness using the flowing equation. 1 over the EC equals 1 over EB plus the D times the K divided by the EP times E. For the EC, we have already determined, and on the previous problem, we know the EB equals 2.2 times 10 to the power of 9 Newton per square meter can be used. However, in a British unit, the EB should equal 3.2 times 10 to the power of 5 pounds per square inch. You can find this value on page 9 in the textbook. And because we know this is ductile iron pipe, so from the table 4.1, we know the EP equals 2.3 times 10 to the power of 7 pounds per square inch. And we know the diameter is 8 inch. And the pipeline is anchored at both ends, so the key equals 1 minus epsilon square equals 1 minus 0.25 square. So the K value is 0.938. You can find this equation on page 126. And now we can determine the thickness E. So 1 over 2.69 times 10 to the power of 5 pounds per square inch equals 1 over 3.2 times 10 to the power of 5 pounds per square inch plus 8 inch times 0.938 divided by 2.3 times 10 to the power of 7 pounds per square inch times E. So now the E equals 0.626 inch. So we have done this problem. The fourth problem is a surge tank problem. We need to determine the diameter of the surge tank if the water in the tank is allowed to rise to an elevation 16.5 feet. So to solve this problem, we need to determine the head loss and the pipeline friction factor first. And we know the minor losses are neglected, so the head loss equals friction loss equals F times L over the D times V squared divided by 2G. And from problem, we know the Q equals 460 cubic feet per second. The diameter of the pipe, D, equals 6.5 feet. So we can know the velocity equals Q divided by top pi times D squared over the 4. So the velocity equals 13.9 feet per second. And we also know the pipe material is smooth concrete, so we know the E equals 0.0006 feet. So the relative roughness equals 0.00092. And the Reynolds number equals D times V divided by the kinematic viscosity. So equals 6.5 feet times 13.9 feet per second. And at the 20 degrees Celsius, the kinematic viscosity of water equals 1.08 times 10 to the power of -5 square feet per second. So the Reynolds number equals 8.37 times 10 to the power of 6. So now we can find that friction factor F equals 0.012. So now the head loss equals 0.012 times the L, length is 3,450 feet. So times 3,450 feet divided by 6.5 feet times 13.9 feet per second square divided by 2g. So the head loss equals 19.1 feet. And therefore, we know key sub F equals HL over the V square. So the value is 19.1 feet divided by the 13.9 feet per square per second square. So the K sub F equals 0.0989 square second per feet. And we also know the damping factor is found using the following this equation: ymax plus HL over the beta equals the natural log of beta over the beta minus y sub mx. And the problem told us that the ymx equals 16.5 feet. So ymx equals 16.5 feet. And we calculated the head loss before. So the head loss equals 19.1 feet. So we can get that beta is approximately equal to 90.9 feet. So we also know that beta equals L times A divided by 2G times K sub F times A sub S. So we know the beta, the pipe A equals pi times d squared over the 4. So the the area of the pipe equals 33.2 square feet, and the length equals 3,450 feet, and the KF we got before is 0.0989 square second per feet, and the beta is this is phi the unit is second square per feet, and we know the beta is 19.9 feet, so we can get that the AS equals 904 feet square. So we can get that the D sub S diameter of the surge tank equals 33.9 feet. So we have done this problem. For the fifth problem, we need to estimate the drawdown, which how many centimeters the lake goes down in the first 2-hour period. If the lake has a surface area of 5,000 square meters, and we know capital P0, the pump output power equals P sub M, the power input to the motor times the E is the overall efficiency of the pump system. And from this problem, we know the PM equals 1000 watts. And we also know the pump system efficiency equals 50%. So we can calculate that P0 equals 500 watts. What also can be described as N times the Newton times meter per second. And we also know P sub 0 equals the gamma times the Q times the HP. From the problem, we know the HP, the total energy had, equals 2.43 meter. And we added the 20 degrees Celsius, the specific weight of water, the gamma, equals 9,790 Newton per cubic meter. And now, because we have calculated the P0, so we can determine the Q now. The Q equals 0.0210 cubic meter per second. And the draw down should equal the volume divided by the area, the surface area of the lake. And the volume equals to the flow rate times the time divided by A. We know the Q, flow rate, equals 0.0210 cubic meter per second, and the time is 2 hours. So T equals 2 hours equals 7,200 seconds. And we also know the surface area of a lake equals 5,000 square meter. So we can calculate that drawdown equals 0.0210 cubic meter per second times 7,200 second over the 5,000 square meter. So the value is 0.0302 meter. So it also equals to 3.02 centimeter. So we have done this problem. For the last problem, we need to determine the power requirement for a motor that is needed to drive the pump installed in a pipeline. And the flow rate in this problem equals 2.05 cubic meter per second from the reservoir A to reservoir B. And the pipe length equals 100 meter, and the diameter of this pipe equals 80 centimeter. And the pipe material is rough concrete, and the water surface of reservoir B is 20 meter higher than the water surface of reservoir A, and the pump efficiency is 80%, and the motor efficiency is 74%. And now we balance energy from reservoir A to reservoir B. And according to the equation 4.2 in the textbook, we know the HA plus HP equals HB plus HL. This is equation 4.2 in the textbook. And for the HA and HB, since the reservoir A and B are exposed to the atmospheric pressure and the velocity head at the reservoir can be neglected, so the total energy head of reservoir A and B equals the water surface elevation. So from the problem, we know the water surface of reservoir B is 20 meters higher than the water surface of reservoir A. So now we know that HB minus HA equals 20 meters. And we know the head loss equals friction loss plus the head loss, minor loss. I consider the two minor loss here. The one is the entries loss and other is exit loss. And assume that the entries the entries is a square edge type, so we know the KE equals 0.5 and the exit loss coefficient equals 1, so KD equals 1. And HF equals F times L over D times V squared over the 2G. And we know the Q equals 2.05 cubic meter per second and the D equals 0.8 meter. So we can get that velocity equals Q divided by pi times D squared over the 4. So the value is 4.08 meter per second. And since the pipe material is rough concrete, so we know the E equals 0.6 millimeter. So we can get that relative roughness equals 0.00075. And the Reynolds number equals D times V divided by the kinematic viscosity. And this value equals 0.8 meter times 4.08 meter per second that we calculated just now. And the kinematic viscosity at 20 degrees Celsius equals 100 times 10 to the power of -6 square meter per second. So we get that the Reynolds number equals 3.26 times 10 to the power of 6. And now we can determine the F. The friction factor equals 0.0185. So now HB equals 20 meter plus 0.0185 times the length, the pipe length equals 100 meter divided by the D 0.8 meter times 4.08 meter per second square divided by 2G and plus the 0.5 times 4 meter per second square divided by OG and plus 1 times 4.08 square of meter divided by OG. And so we can 2G, so we can get that HP equals 23.2 meter. And we also know that the capital P 0, the pump output power equals the gamma times Q times HP, so equals 9790 Newton per cubic meter times 2.05 cubic meter per second times 23.2 meter. So the pump output power equals 466 kilowatts. And we also know that the power input to the motor P sub n equals the pump output power capital P sub 0 divided by the E. E is the overall efficiency of the pump system, and E also equals to the EP times the EM. From the problem, we know the EP equals 80% and EM equals 74%. So the EP equals 80%, the EM equals 74%. And we know the P0 equals 466 kilowatts. So we can determine the power input to the motor. PM equals 466 kilowatts divided by 0.8 times 0.74. So the value is 787 kilowatt. So we finished this problem.